Hi, welcome to lecture 5.4, integration by parts. So last time we talked about how we're going to start doing lots of antiderivatives, and we're going to need specific rules to take certain antiderivatives. We talked about U substitution already. That was one of our main tricks, but integration by parts is sort of trick number 2, the second most important one. So whenever you see a new antiderivative, U sub is the first thing to try, but very often integration by parts is the next thing to try. How I'm going to do this is first I'm just going to talk through sort of where this integration by parts comes from, and then we'll see like a formula version where it's kind of streamlined, and then we'll see an even more streamlined version near the end. So we might remember that when we did U sub, we talked about how it comes out of the chain rule, right? We have this chain rule when we do derivatives, and so we did the chain rule backwards in a certain sense to do U sub. So similar things happening with integration by parts. So let's remember the product rule from taking derivatives. We're going to see in a minute sort of how to do product rule backwards in a useful way. So let's remember the product rule. It says if I have the product of two functions, f times g, and I'm going to take the derivative, remember the prime means derivative, I can take the derivative of the first part, f prime, multiply it by g, and then take the derivative of the second part, g prime, and multiply by f, and then add those together. So let's see an example. So if this is our function, x squared times e to the x, I can do x squared e to the x. I want to find its derivative, so I'm just going to kind of follow my template here. First do the derivative of the first part. So I'm going to write it like this just to kind of see the structure, even if you know what that derivative is already, times the second part, e to the x, plus the derivative of the second part, and then times the first part. By the way, you might remember doing it this way. So that's exactly the same thing. I just changed the order here. If that makes more sense to you, you can do it that way. Same thing. So now we can do our derivatives. So derivative of x squared is 2x. This is just e to the x. This is the derivative of e to the x is e to the x. So something that's interesting about this calculation is that say we were looking at like this guy right here. Say I was asking you to do the antiderivative of 2x e to the x. So remember, that's looking for a function, looking for something, who, when I take its derivative, I get 2x e to the x. That's what it would mean to find an antiderivative. So we've done something here. We found a function whose derivative is not exactly 2x e to the x, but its derivative includes 2x e to the x. So if we were thinking hard about how to come up with an antiderivative, we might think of, well, maybe we could start with something like this. When we take its derivative, the thing I'm looking for will pop out, maybe plus something else. So that's kind of the beginnings of an idea if you were sort of inventing this for the first time. Let's see that same idea maybe in a second example. Also just kind of recalling how the product rule works. So the derivative of x times log x. So I'm just going to do it kind of faster this time. So we have the derivative of x, so x prime, times log x, plus the first part times the derivative of the second part. So whatever log x's derivative is. I guess I could put parentheses here too. So x's derivative is 1, ln is ln, x is x, and then the derivative of ln, remember that is 1 over x. So that's one of the rules we're supposed to know. And we can simplify this. I'm going to get ln x plus, and this is 1 here. So again, if I was maybe thinking about an antiderivative of log x, one place to start would be looking at this expression, because through the product rule, I know its derivative ends up including the log x and this other thing. So we'll see how this works exactly in just a second. Okay, so we're going to try to think about reversing this process. So let's kind of follow this chain of thought a little bit more. Say we were trying to find the antiderivative of this guy, x squared log x. Question would be, could we think of an expression whose derivative happens to contain the x squared log x? So that means, can I think of something whose derivative contains my x squared log x? So maybe it's equals some question mark and then maybe plus an x squared log x. So we just saw a bunch of examples where when I take a derivative of a product, I get something plus something. So maybe it would make sense to try to think of some f and g, some two functions, whose derivative of their product ends up being this. And remember the product rule that we had on the last page, f prime g plus f g prime. So if this is going to pop outside, one way that could happen would be if this x squared ended up being the f prime and the log x ended up being the g. So why is that helpful? Well, the thing is, if I'm looking at x squared, I know what f would be if x squared is f prime, right? I know that x cubed, right, x cubed over 3 is something whose derivative is x squared, right? This would be 3x squared over 3. The 3's cancel. So maybe I could have started with x cubed over 3 times log x. When I take its derivative, I bet this expression will pop out. So let's try. I'm going to have, so x cubed over 3, so that's just keeping that, times the derivative of the second part, so the derivative of ln x is 1 over x, plus take the derivative of the first part, so the derivative of x cubed over 3 is x squared, and then keep the second part, ln x. So that's ln. So cool. Expression I was looking for sort of popped out, but there was kind of this cost of having this guy right here. By the way, we can simplify this. It's 1/3 just x squared, right? There's 3 x's in the top, 1 in the bottom, and they cancel. So let's step back and take a look at what we found here. We found that if I take x cubed over 3 times ln x, and I take its derivative, I ended up with this right-hand side. So remember, our original goal was finding the antiderivative of x squared log x. One of the most powerful rules we learned about antiderivatives and integrals is that you can integrate the sum of two things by integrating each part separately. Right? If I do integral of f plus g, that's the same as integrating f plus integrating g. That's helpful here because of this left side, I have the derivative of something. Right? That's what this says. It's something prime. So something I could imagine doing is taking the antiderivative of the left side and also taking the antiderivative of the right side. On the left side, so that's a move you're allowed to do. I can always take the antiderivative of both sides of an equation. On the left side, I have the antiderivative of some derivative, so I just keep the original inside. Right? What's the antiderivative of the derivative of something? Just the original something. And on the right-hand side, because of this adding thing, I'm going to have the antiderivative of the first part plus the antiderivative of the second part. And now, all of a sudden, we are onto something. Because I have this as part of my equation, that's the thing I was looking for. If I can just rearrange this equation, I can have this antiderivative equals. Right? Let's see what this looks like. If I just subtract, so let's copy this. If I subtract this from both sides, then what's going to happen is I'll have my antiderivative that I'm looking for equals whatever is left over. So I have the x cubed over 3 log x, that's here. Then I'm subtracting this integral of this antiderivative. So as long as we can kind of figure out what this right-hand side is, this right-hand side, like, it is the antiderivative of what we started with. That's super cool. Right, so we're using this linearity here, using the fact that you can integrate by the sum of two things by integrating each part separately and then adding them up. It means that if I'm starting with something whose derivative includes in the sum the thing I'm looking for, because I can antiderivative each side, I can actually like solve for the antiderivative I'm looking for, which is pretty cool. By the way, we can simplify this over here. We'll just keep this. But we already know maybe what this is, right? The 1/3 can come out. That's one of our rules. And then x squared, I know the antiderivative of that already. We did that earlier. It's x cubed over 3. So this is a perfectly good antiderivative of what we started with. You could double check that if you took the derivative of this, you would get back to what we started with. Okay, so I know that was kind of fast, but I'm just kind of trying to give you an idea of maybe where you would start thinking about this. I'm going to do one more example really quick, and then we'll kind of see a more, like how to turn this into a useful formula. So let's take a look at this one. Same idea. Let's say I was doing the antiderivative of x sine x. That would mean I'm looking for some two functions. Well, so that would mean if I'm trying this technique that we're thinking about, look for two functions who I take the product, I take the derivative, and I somehow end up with something plus x sine of x. So a way that could happen is to say, okay, maybe this x was my f, and this sine x was my g prime. Remember, the right-hand side has to be the sum of two things, so maybe one of the things, I'm just sort of guessing, right? I don't really know for sure, but I'm guessing that this x sine x term is this part, the f g prime. We'll see in a minute that there is a little bit of guesswork sometimes, but there's only usually so many choices to make. So if this was our f and our g prime, then that would mean my original thing would have to be, well, f times g, so this, f is x. If g prime is sine, what could g have been? I need something whose derivative is sine, so probably like cosine, right? Now I could say negative cosine, right? I actually know that sine's derivative is cosine, and cosine's derivative is negative sine. So if I want to end up with a sine after I take a derivative, I should really start with negative cosine. But we'll see here that it doesn't actually matter, and it's just a little bit easier. I don't have to put the negative sign inside here. So it'll be fine to use just cosine here. So, okay, so maybe that was my f times g. Let's see what its derivative would be. So derivative of the first part is 1, and then keep the cosine, and then keep the x, and take the derivative of the cosine, so negative sine. Okay, now let's use that same trick that we did before. I imagine integrating, or taking the antiderivative of both sides, which is a move you're allowed to make. On the left, we have the inside, x times cosine x. And on the right, I have, well, by breaking it up across the plus sign, I have the antiderivative of cosine, whatever that is. And then I'm going to say minus, because I can pull this minus sign out, minus the antiderivative of x times sine of x. Okay, this is exciting, right? We were trying to find the antiderivative of x sine x. This right here is the antiderivative of x sine x. All I have to do is rearrange this equation, and I'll have that this equals something. So the fastest way to do this is to actually to add this one over here, and then subtract this one over here. So let's see what that looks like. If I add the integral, the antiderivative, I'll have antiderivative x sine x dx. So I'm adding that onto the left side. On the right side, I'm keeping my antiderivative of cosine, but then I'm subtracting the x cosine x. So I did that a little fast, but just double check that algebra. A good algebra shortcut here, if I ever have like a equals b minus c, I can always swap that to like c equals b minus a. Like the c and the a can switch places just by adding the c over and then subtracting the a over. Okay, and we know this part. We know the antiderivative of cosine. It's sine. So we discovered that in fact the antiderivative of what we started with, x sine x, is actually this thing. Sort of by doing this trick and isolating. So that's like a cool idea. We can imagine writing all that we just did just a little bit more abstractly. I'm going to use placeholder names for the functions instead of what we started with. Okay, instead of like a specific example. So if you're kind of inventing, discovering math, this is the kind of thing you think about. I did a bunch of examples. Let's see if I can sort of imitate what was going on, but maybe with something generic instead. So I'm going to use u and v just because that's traditional for integration by parts, but they're just like the f and g that we had before. They're just names of some functions. So imagine we had two functions, u and v. I multiply them and I take the derivative. What happens is I get product rule. Derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. In both of the examples above, what we did after that is we sort of took the antiderivative of both sides. On the left side, we had our original product left over, u times v. I'll just write it like that. Remember, whenever you just put two things next to each other, that means times. And on the right side, by splitting it up, I have antiderivative of uv dx plus the antiderivative of u v prime dx. Now, there's just a little thing here with the dx's and everything, which is weird because I have u's and v's and I have x's, but I'm imagining that u is like some function of x and v is some function of x, right? Right, normally I write like f of x. So if u is some function of x, then there's really like x's in here. I just don't know exactly what they are. But I can still think about the derivative, right? Like when I write u prime of x, that's just short for this notation, du dx. And v prime is dv dx. So let's just imagine replacing those in here. So let's say u prime, that's du dx, and I have a v sitting here, and I have a dx. And then over here I have u, and then v prime is dv dx, and I have dx. So the reason I'm writing it this way is that it's useful to imagine that in this expression, this dx and this dx sort of cancel out, because like one's on the top and one's on the bottom. What would be left is v du. On the right hand, this dx and this dx sort of cancel, and there'd be a u dv. So I write that. So this is sort of something that as your calculus teacher, I'm officially supposed to tell you that this is technically not a legitimate thing. dv dx, like these guys, are not fractions, technically, and you can't really cancel the top and bottom like this. However, historically it was thought of that way, and in many cases it sort of ends up working out if you use the notation like that. So this is mostly meant to be suggestive, so don't worry too much about it. We're just going to kind of use the formula pretty soon. But talk to me if you're curious about that. There's secretly a fundamental theorem of calculus happening because I have like a derivative inside an integral. So you can make it a little more rigorous, but this is one way to think about it, that these dx's sort of cancel. So let's see what this looks like. Remember, my goal, right, was usually to try to integrate something. So I'm just going to rearrange this, and this will not look super motivated right away, but we did make this rearrangement in both of our examples before. Take this guy, get him by himself, and then I'm going to subtract this over. So I'll have uv minus integral v du. Okay, so this is the classic integration by parts formula, and we're going to use it a bunch. So I just kind of wanted to give an idea of it comes out of doing the product rule. This is going to be useful to find integrals when this integral on the left-hand side looks like the product of two things. I'm going to be having integrals like we had before, x squared log x dx, and I'm going to be identifying, okay, u, this is going to be the u, and then the dv, this whole thing is going to be the dv, including the dx. So log x, like I could write log x dx equals dv, and I would write u equals x squared. Turns out that just notationally, that's a useful way to write it. We can manipulate these expressions to get the stuff on the right-hand side in order to figure out what this antiderivative is. It's going to be the most useful when, like in our last couple examples, like the classic example of by parts is when it's a product of two things that you know a lot about. Like I know about x squared, I know about log x, I know about x, I know about sine. But when it's a product of two familiar functions, is the most common time we're going to use by parts, integration by parts. Okay, so you don't have to know this story that I told, the derivation. We're mostly going to be using it, but I did want to give you some idea of where it's coming from. So let's take a look at sort of the quote-unquote book method, integration by parts method. So, like I said, given an integral, as long as you can recognize it as something times something, where the second something has the dx in it, then we can use this formula, and I will show you a great way to organize your work. So let's take a look at this one. We will talk about, right, so I'm going to identify parts of this antiderivative as my u and my dv, and then I'm going to manipulate those. We will talk in a minute about what's a good strategy for choosing your u's and your dv's. For now, I'm just going to tell you that we're going to do u is ln x and dv is x dx. What I want to highlight here is that the order can change, right? I've decided that dv was going to be the x dx part multiplied together. That's fine. It doesn't have to like all be in a row. And I decided that this is going to be the u. Again, there are only so many choices. It's good to try different choices. I could do u equals x and dv equals log x dx. And there's a couple other things you could try. Let's just see how this one works out first. But know that you could try other things. Whatever you pick for dv is you're supposed to write it with this dx right here. It's a helpful notational thing. We'll see why in a second. Okay, so I've identified my u and my dv. I know this side of the formula. I can pretty much just write down what the answer is going to be. I just need to figure out what all these different pieces are. I have u. Okay, great. I need v. Where am I going to get v? Well, I have dv right here. So I want to think of this as like the derivative of v. I want to come up with a v whose derivative is x. So I'm basically doing an antiderivative right here. So what's an antiderivative of x? Well, maybe x squared over 2, right? That's something whose derivative ends up being x. It's 2x, and then the 2 cancels. You might remember that like when we do u sub, I would write something like this, and then I would put a d on the left side, and then I tell you you're supposed to write the dx over here. That's kind of the same notation as what's going on here, but we're doing it backwards. So I'm starting with something that has the dx tacked on. I go backwards by doing an antiderivative. So, okay, so we've got our u, we got our v, nice. We've got half the answer. We just need v, okay, we got that. And we need du. Where's my du coming from? Probably from the u, right? I have the u. Where do I get du? Well, just like with u sub, I can just write du, take the derivative over here. The derivative is 1 over x dx. And I'm supposed to write the dx. The dx thing is mostly just a notation. When we assemble our integral in a second, you will see that it kind of makes it write itself in a nice way. Okay, now that we've identified all our pieces, we just have to string them together. I can say that our original integral is equal to uv, uv minus integral v du. I just have to fill in the pieces. U is ln x. V is x squared over 2. And then minus integral v is x squared over 2. And then du is 1 over x dx. Right, so you see what's happening with this dx. Because I just said du is 1 over x dx, when I go to write du here, the dx just comes along and it automatically like completes the antiderivative notation. If you didn't have it, you would just have this, which is maybe fine, but we want to like have the dx here to remember that we're integrating, we're doing it with respect to x. Okay, so we're done basically, right? So like we wrote out the right hand side. That is the antiderivative. The only final step maybe would be to simplify things, and there's typically going to be another antiderivative sitting here. Typically, always, that's part of the formula. But the hope is that that's like an easier one to do than we started with. So we're always going to have to do this second integral, but we kind of make it more simpler the second one is simpler than the first one. So let's do this second integral. Notice, first of all, that we can pull the 1/2 out. 2 in the bottom is the same as 1/2 out front. X squared on the top and x on the bottom, 1x will cancel. There'll be x left over. And that's something that I know, right? Keep the 1/2, and then x goes to x squared over 2. And then I can simplify. This is x squared over 4, because the 2's in the bottom can cancel, or combine. So that means in the end, our antiderivative that we're looking for, final answer, so we have our log x, x squared over 2, minus what? Minus the thing we got here. Cool. So that is our solution to this one. So, so this notation here is a little bit funny, but it's traditional, and it's pretty useful for just sort of plugging and chugging and getting the right answer. If you're interested, I would encourage you to think about how this is like a streamlined version of this sort of argument we were doing up here. I guess we're really just using this formula, but yeah, I recommend writing the u and dv sort of organized exactly in this way. So let's try the next one. Go a little bit faster because we know the method now. Okay, so we need our integration by parts formula. Integral u dv is uv minus integral v du. So I just got to identify u's and v's. So again, we haven't talked about how you would pick a good one, but let's just pick u as log x, and then dv is x to the 100 dx. I will mention right away that like the plan with u and dv is to find du and to find v, right? So whatever you pick for u should be something that you know what its derivative is. If I pick something weird here that I didn't know the derivative, then I would get stuck, because my first step is to take its derivative. So it definitely has to be something whose derivative you know, and we're supposed to write dx. Similarly, the dv you pick better be something that you know the antiderivative of, because the plan is to do the antiderivative right here. So like if I'd picked dv to be log x, then I actually get stuck because I don't know what the antiderivative of log x is. I mean, maybe we'll know at some point, but it's not in our tool bag yet. Okay, so yeah, we pick our u, pick our dv, we take the derivative here, we take the antiderivative here. What are we going to get? Remember, we do plus 1, so it's x for x to the 100, we'd go x to the 101 over the new denominator, 101, and the dx is gone. Okay, so now we just got to assemble everything together. I'll go ahead and show you right now. If you write the u and the dv exactly like this, where u is here, dv is here, du is here, and v is there, then you get a nice little shortcut which is that the formula is this zigzag. It's a little funny, but this is the way I kind of learned it, and it makes sense to me. If you just remember to start with u and dv, then take the derivative, take the antiderivative, then you get the zigzag. U times v minus the antiderivative of v du. So u times v, so that's log x times v, x to the 101 over 101, minus antiderivative of what? V du. So v is x to the 101 over 101, and then du is 1 over x dx. So this is equal to that. I'll just write, yeah, equals that. So again, we're basically done. We just have to maybe do this final integral. Let's see what it is. Remember, we can pull the 101 out. It's the same as 101 in the bottom. One of the x's will cancel. I'll get x to the 100 dx. And I know the antiderivative of that. In fact, we just did it basically, right? I'm going to plus 1 and then keep it. So we'll have this sort of extra factor on the bottom, but that's okay. Our final answer is going to be log x times x to the 101 over 101 minus the result of this mini subintegral, which was x to the 101, and then over whatever 101 times 101 is. I'd be happy if you left it like that. Okay, cool. So we're hopefully getting an idea of sort of how it works. You pick a u, you pick a dv, you do the thing, you do your zigzag, and maybe you do this last integral. If you pick maybe the wrong quote unquote u and dv, like you pick a u that doesn't seem to work, like you take the derivative, either you don't know how to take the derivative, or after you do it, like this integral is too hard or something, then that's okay. You just back up and you try a different u and dv. In a given integral, there's only so many options, right? Like, there's only so many algebra chunks here that you could possibly grab to pick. And we'll see in a minute sort of like a recommended strategy. Okay, something I should mention about this is the bounds. So if we have a definite integral like this, remember the plan is to take an antiderivative and then plug in 5 and 1 and subtract them. That's the plan. So step 1 is to take the antiderivative. This is a great example of a by parts problem, and at the end we'll see how we have to plug in the bounds as well. So we'll pick, again, I don't know why yet, but we'll pick u as x, du is 1 dx. So I just took the derivative. dv is e to the x dx. And yeah, I'm going a little fast here just because we've done it a few times. The antiderivative of e to the x is e to the x. Now I can do my zigzag thing. U times v is x e to the x minus the antiderivative of v du. So that's e to the x times 1 dx. So I can just write dx. By the way, we know what this is. The antiderivative of e to the x is e to the x. Okay, so what we found is that the antiderivative of x e to the x is, apparently, x e to the x minus e to the x. How does that help me with my original problem? Right, we're not actually being asked to do an antiderivative, we're being asked to do a definite integral. But to do a definite integral, we first find the antiderivative, right? And then we plug our numbers in. So the answer to the original question is going to be, okay, take x e to the x minus e to the x, which is the antiderivative I found, but then we're going to plug in 5 and 1. So we plug in 5 and 1 and we subtract them. So I'll get 5 e to the 5 minus e, or that's a 5. 5 e to the 5 minus e to the 5. And then that's the first part. Subtract the second part where I've plugged in 1. So 1 e to the 1 is just e to the 1 is just e. I guess I'll write 1 e to the 1. So we can simplify that. This is 5e to the 5 minus e to the 5. And this is 0. So we just get that. And then 5 of them minus 1 of them is 4 of them. So that's apparently the answer. The main point here is that we have to plug the 5 and the 1 into this part as well. Right? It's pretty natural to imagine if I just told you to write 5 and 1 there on this second integral that we get. But it's really easy to forget that the 5 and the 1 are also like applying to this x e to the x part. So I like to think of it as just you find the antiderivative of the whole thing, and then at the end you plug the 5 and the 1 in. But we do have to do that if we're doing a definite integral. Okay, cool. So another thing that can happen with integration by parts is sometimes you have to do it more than once. Why would I do it more than once? Well, because maybe this second integral I get is also a harder integral that you'd have to do by parts to do, maybe. So let's see what that might look like. Okay, so this example is the antiderivative of x squared e to the x. So I claim that a good u to pick is u is x squared, dv is e to the x, dx. Now we take the derivative here, 2x dx, and we take the antiderivative here, v equals e to the x. That's the antiderivative of e to the x. I do my zigzag thing. We're going to get that the antiderivative of the original is what? U times v minus the integral of v du. So e to the x is v, and then du is 2x dx. Okay, so normally we'd have to do this integral somehow. But this one, it's not super obvious how to do it. Like, it's not like this one where it was just e to the x. It's a new integral that's kind of hard, right? There's an e to the x, there's an x. In fact, this is another candidate for integration by parts. Sometimes you have to do this integral, the second integral, somehow. Like, you always have to do it. Maybe it's a u sub. Maybe it's one of the techniques we'll learn later. Maybe it's another integration by parts. So it's not always like necessarily another integration by parts, but it's a fairly common pattern where the second integral ends up also actually being a by parts integral. First of all, let's go ahead and subtract this, pull the 2 out, because you can do that, and it just makes it look a little bit simpler inside here. Now, it's easy to sort of lose track of what's going on because we have a lot of integrals floating around. What I like to do is sort of just take this guy, make like new subproblem, and then we'll kind of come back and fill it in at the end. So new subproblem, how would I do the antiderivative of e to the x times x? Well, let's try integration by parts like we said. Now, this is going to start giving a hint of what a good u and v to pick would be. Like we saw before that if I picked u as x squared, the du maybe like it made the integral simpler, right? We had an x squared e to the x. After our by parts, we got this new antiderivative, which is e to the x times just x. Right? Before we had x squared e to the x, and now we just have x e to the x. It seems like that's happening because this x squared maybe got simpler. It turned into a 2x. The power went down. So when I pick u to be like x to the something, it's going to get smaller. The du will be small, like a smaller power, and often that's a good idea. Let's just kind of roll with that and see what happens if we pick u to be x again. Also, this dv is something we know how to take the antiderivative of. Okay, so du will be 1 dx, so you can just write dx, and v will be e to the x. It's the antiderivative. Okay, so now we do the zigzag. U times v, so this integral is equal to x e to the x minus the integral v du. So e to the x and then du is dx, so e to the x dx. Now this, mercifully, is one we know how to do. Theoretically, it could be another random integral. Maybe another by parts, maybe something else. So in this case, we only had to do integration by parts twice, but it can happen multiple times. So here the antiderivative is just e to the x. Okay, so this thing, we actually did this one earlier basically, is the result of this integral. So when I come back up here, I want to plug this directly into that slot. So I keep my x squared e to the x from before, I keep the minus 2, but then I have a slot to put my result in. My result is x e to the x minus e to the x. It's important to be careful about this because there's a lot of minus signs floating around and it's easy to get confused. So I like to kind of draw these big parentheses, sort of black box that I'm going to put some chunk of algebra that I just found. It might have its own minus sign, and that is a little bit helpful. Okay, so the last step here is just simplifying a little bit. I can distribute this 2 through, so it's minus 2x e to the x, and then plus, because there's two minuses, plus 2e to the x. Cool, and that's like final answer. You might wonder sometimes about how far should we simplify. Here you could pull an e to the x out because there's an e to the x in each term. And this is kind of nice because then now it's e to the x times a quadratic. But either of these would be fine. Okay, so sometimes you have to do it more than once. Okay, so last couple things I want to talk about. First, just some guidelines for picking u and dv. And then second, a kind of cool, super fast way to do this, which I cannot help but show off. I think it's good to see. Okay, so first of all, this so-called Liate guideline. So the guideline is, when you're picking your u, try prioritizing in the following order. If you see something with a log or ln, maybe that's a good u. Try that first. If you see inverse trig, like arcsine, that's sort of candidate number 2 to be a u. And so on. Algebraic means something with x's and powers and roots and stuff like that. Trig means like sine and cosine. And exponential means like e to the x, or 2 to the x. So this is not like a real like hard and fast rule or anything, but if you are in doubt, it's worth trying this first. The main principle here really is just, like I mentioned earlier, picking something for u that's like easy to take the derivative of. All right, log is easy to take the derivative of. The other part has to be something that you can take the antiderivative of. So like logs are sort of hard to take the antiderivative of. So this is not a super, like I said, it's not a ironclad, but it's pretty good. So for example, we saw this one earlier, but here I see an x, I see an ln. So my priority list here says, okay, there's a log. Okay, so I'll try u equals log x, and just see what happens. So this is just a guess, really. As you do more and more by parts, you will get a sense for what is a good u and dv. This is a good starting guideline. dv would have to be the rest of it, x dx. And then we find our du, it's the derivative of this, 1 over x dx. And then v here would be antiderivative, so x squared over 2. Now I do my zigzag. So this equals, the antiderivative equals u times v. So log x times x squared over 2 minus the antiderivative of v du. So that's x squared over 2 times 1 over x dx. So I think we had the same setup before. That's going to end up working out. Okay, cool. So the one more thing I want to show off is something interesting that happens with certain integration by partses, and we will see a sort of table method, I call it, which makes use of that. So let's just take a look at this example. So I want to do this antiderivative. Let's try u equals sine y. Well, it is following the Lyautey rule. I try sine before I try exponential, and the only other thing in here is the e to the x. Also, I know the derivative of sine, it's like pretty easy, and I know the antiderivative of e to the x, that's also pretty easy. Now, I know the antiderivative of sine also, but let's just go with this because that's what the Lyautey rule suggests. So I do my du is cosine x dx, and then my v would have to be e to the x. Okay, so let's write it down. So this is u dv. It's going to be equal to, so zigzag, uv, so e to the x times sine x. I changed the order, it doesn't matter. Integral v du, e to the x cosine x dx. Okay, so now we're supposed to do this one, right? It looks an awful lot like the original one. It's a cosine instead of a sine, but I know that the sine and cosines, like derivatives, work pretty similarly. Let's do subproblem here. How would I do this guy? Well, I'd probably say, let's just try the same thing, right? Lyautey suggests u is cosine, du would be negative sine, and dv would be the rest of it, e to the x dx, and v would be e to the x. I do my zigzag, and I get e to the x times cosine x minus the antiderivative. Minus the antiderivative of e to the x times negative sine of x dx. So that's e to the x cosine x. So there's two minus signs here, so I can just write plus integral e to the x sine of x. Okay, so you might already have a suspicion where this is going, but let's just see. So my original antiderivative is e to the x sine x minus what? Minus this thing that I found over here. So minus that whole thing means minus e to the x cosine x minus the antiderivative of e to the x sine x. I'll write this here just for clarity. Okay, so I want you to stare at this equation for a few seconds and think if you have any super clever ideas about how to like get a final answer for what this antiderivative is. Sorry. So what's interesting here is that this thing I'm interested in, this final answer for what's this antiderivative, that antiderivative itself, in fact, appears on the right-hand side. Like whatever these things are, they're the same thing. That's actually sort of interesting, because what would happen if I added this over, added that on both sides? On the left side, now I'd have two of those integrals, right? If I just add the copy of it over, I'd have two of them, which I can write like that. But on the right-hand side, now I have this leftover stuff. That's unchanged. Oh, wait a minute, we're done, right? I was trying to figure out what the antiderivative of e to the x sine x was. I can divide by 2 now. It's apparently half of this stuff. So that thing on the right-hand side, and then just divide it by 2. So it's a little weird, right? The original antiderivative popped out after doing sort of 2 sets of this integration by parts. We could move that antiderivative over to the left side and sort of solve for it. So it's just kind of like a little algebra quirk that happens sometimes, but it's pretty weird if you haven't seen it before, so I just wanted to show that off. The main thing here to think about sort of algebra-wise is it's good to be comfortable, like even though, like don't think of this equals as like getting me closer to the answer. Think of it as a sentence where I have this thing on the left is the same thing as this thing on the right. And so like this thing, which is the final answer I'm looking for, is also like a chunk of algebra that can be manipulated. I can add it over to the other side and maybe solve for it if I want to. So that's a useful example. Okay, one last thing I want to show off about integration by parts is what I call the table method. So let's look at this. So this is really useful when you have repeated integration by parts. So look at this antiderivative. It's the antiderivative of x to the 5 e to the x. So let's imagine we follow the Liate rule. Liate suggests that my first should be the x to the 5, and the dv should be e to the x dx. Why does it suggest that? The x to the 5 counts as algebraic. That's ahead of e to the x, which is exponential. So let's say we pick that. What would be my du? 5x to the 4 dx. What would v be? E to the x. Okay. If we set this up, we would have our original antiderivative is x to the 5 e to the x minus an integral e to the x and then 5x to the 4 dx. Right, and then the plan is to do this integral next, right? How am I going to do that integral? Probably by parts. I would pick maybe u equals, Liate suggests, 5x to the 4. dv would be e to the x dx. I do it again. 20 x to the 3, so 4 times 5, right? dx. V is e to the x. So what I want you to notice here is that the u that we picked the second time around doing the integral, this 5x to the 4, is exactly the result of doing the du originally. Right, the du, the 5x to the 4, ended up being the new u that I picked when I did the next integral. And the dv ended up being the v from the previous one. So what happens is that, like, you know, if I was to imagine, like, taking this integration by parts setup and moving it over here, right? The last step of the previous one and the first step of the next one, like, totally line up and they're like the same thing. So what that suggests is that instead of like kind of writing this all out like this, I could just take this derivative and then sort of skip a step and take a derivative to again to get to here, right? The 5x to the 4 turns into the 20x to the 3. And simultaneously take the antiderivative right here. And maybe why not keep going, right? Maybe why not take the derivative again to get 60 x squared and then e to the x. And then maybe again to get 120 x and e to the x. And so the crazy thing about this is that this turns out to work actually. So you have to be a little bit careful with like the minus signs and stuff. But this is a cool shortcut. If I was to do this integration by parts the long way, it would take like several pages of work because I'm doing like this and then doing by parts on this one. I get two things again. This one would be an integral. I do by parts again. I get two things again. This one would be an integral. I do parts again. It would take forever. But it's like super duper fast with this like table method. So let's see a short way to write this. So what I do is I just write a u here to just remember that I have my starting u, x to the 5. And then I have a dv here, which is my starting dv. And now I just take derivatives in the left column until until I'm done, as long as I can go, right? So the first derivative, 5x to the 4, and then I take the derivative again, I get 20x cubed. Derivative again is 60x squared, and then 120x, and then 120, and then one more. The derivative of 120 constant is 0. So this is like 6 rows of integration by parts or whatever. On the right side, I take antiderivatives. So e to the x, 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 e to the x. And I could keep going, except we'll see in a second that we will need to stop at the 0 here. Now, remember my zigzag move from before? It turns out, I'm not going to show exactly. You can think about it if you're curious. But it turns out that when we do this like stacking another by parts on the next one thing, the way the minus signs work out is that instead of doing a single zigzag like this, I kind of do products as I go, and then the very last step I do a zigzag. So I'll show you what I mean exactly in a second. So the antiderivative of what we started with is these products all added up. So the product of the first zig, I guess, x to the 5 times e to the x. And then the product of the next one is 5x to the 4 times e to the x. And then 20x cubed times e to the x, 60x squared times e to the x, 120x times e to the x, 120 times e to the x. And then the very final step is the integral, the antiderivative, of e to the x times 0. Which you can maybe guess what that's going to be. I'm basically just going to add these all up. And that's going to be my final answer. Because of the minus signs, right, when we do the by parts, we always get something minus this thing. Every time, every row that you do, there's like another minus sign. So you have to keep track of those. It turns out what's correct is to just alternate. So the first term is a positive, but then it's minus, plus, minus, plus, minus, plus. So I remember this by just remembering it's alternating here. So the regular by parts, maybe like if we did x ln x, right? I could is in this format. I could have x, so for my u, dv, x. Actually, sorry, I want x to be log x, or u to be log x, and dv to be x. I take my antiderivative, or take my derivative, 1 over x, x squared over 2. And then my zigzag is sort of just a one-step version of this thing. I'd have a plus and a minus. By the way, this last one here, I didn't get back to this. So integral of e to the x times 0, that's just the integral of 0, and that's just 0. So that's actually really nice. So if you can actually take derivatives and get down to 0 here, then that actually kills the very last step. You don't even have to do another antiderivative at the end. In this little example I did here, we do have to do another antiderivative at the end. So it's log x, x squared over 2, and then minus, because of the minus sign, the integral, that product, 1 over x times x squared over 2, which is easy after you simplify it. But yeah, if you can get all the way to 0 over here, then you actually don't even have to do that antiderivative. So it's pretty powerful, and I just can't resist showing it off because this would be crazy to do like through 2 or 3 pages of normal by parts. What's kind of nice also is if this makes sense to you, you can even just use it on regular by parts like we did right here. Like so for example, and like you can do it pretty fast if you're comfortable with it. So like for example, say try this one using the table method. Remember, this was the one we did a minute ago, right? This one that took a few minutes and we had this weird like go into the other side thing. Let's see what happens if we try it on this one. So let's just have the same setup we did before. where I had u be sine, dv be e to the x. We take the derivative over here, we take the antiderivative over here, take the derivative over here, antiderivative over here. And it's tempting to keep going, right? But what's going to happen? We loop back to where we started, right? I hit sine here, and then I hit cosine, and I'm just going to keep going. I'm going to keep looping forever. So it's good, it's nice if you can get to 0 because you stop, but sometimes you don't ever get to 0 and you would just go forever, or something else happens that's not helpful. So what that says is, well, let's maybe stop. Maybe we could stop at the second row, but let's maybe stop at the third row, because it's promising that I see the same, like this last zag going to the right. That's the integral sine e to the x. That's familiar. That's the original antiderivative. And the same sort of trick that happened before is going to work. And so it's the same thing we did before, just written a little bit faster. Integral e to the x sine x. So I have to remember my plus minus plus thing. So I just write it down. It's sine x e to the x. That's the first one. Minus cosine x e to the x. That's the second one. And then minus, because there's a plus and a minus, the integral of the last product, sine x e to the x. So, and just as long as this makes sense, in just a few seconds, you can kind of write down the whole thing without having to do like a second by part step explicitly. And again, just like before, we can add this over, and we'll get our final answer. And that's the same as before. I want to just go back and look at the other ones that we did, just with this table method also, just to make it clear. Let's maybe try this one. So we can just have a little bit of space because it's pretty efficient. So let's have u be ln x. Then I'm going to take a derivative. Let's have dv be x to the 100. Take an antiderivative. And again, we could keep going, right? I could take the derivative of 1 over x. It'd be like negative x to the minus 2 or whatever. But that seems like it's not getting more simple. Before we got all the way to 0 because my powers just kept going down. But here I already have like a negative power, like this is x to the minus 1. So it seems like the powers are not going to get more simple as we go down. And I know that if I stop here, this second zag, its integral, I'm going to be canceling the x to the 100 with the x on the bottom. That sounds like an integral that I can do. So I can just write it down. Log x to the 101 over 101, that's the first product, minus the integral of the second product, or the last product. It's the exact same thing we got before, and that's something we can do. So it's not really any different than, so you just compare how we wrote this. It's the same thing. It's just a little bit sort of cleaner and is useful if you have multiple by parts to do in a row like we did in this situation. Okay, so I think that's everything I wanted to say about by parts. Let me know if you have any questions, and I will see you in the next lecture.